Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at REGENESIS and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. In today's presentation, we'll focus on a next-generation approach to complex contaminated sites. With that, I'd like to introduce our presenters for today. We are pleased to have with us today Rick Cramer, California Remediation Department Manager at Burns & McDonnell. Rick is a California licensed professional geologist with over 30 years of environmental experience and serves as the Remediation Department Manager and Environmental Sequence Stratigraphy Practice Lead with Burns & McDonnell out of their Brea, California office. He began his professional career in the petroleum industry and pioneered the application of sequence stratigraphy to groundwater projects. We're also pleased to have with us today John Hesemann, Remediation Technical Practice Leader at Burns & McDonnell. John is a licensed professional engineer in 7 states with over 21 years of environmental experience. He has personally led or supported over 100 remediation projects in 17 states, mostly for industrial clients managing risks associated with chlorinated solvents, petroleum compounds, and other recalcitrant contaminants. We are also pleased to have with us today Craig Sandefur, Vice President of Remedial Applications Development at REGENESIS. Craig has over 20 years of experience in in-situ groundwater remediation, with expertise in the areas of remedial design and applications. In his current role at REGENESIS, he is part of a team of geologists located throughout the United States, providing remediation designs and optimized performance for REGENESIS clients. Under his direction, REGENESIS developed its Pre-Application Design Verification Testing Program, or DVT, which has resulted in improved remedial reagent emplacement, improved remediation project outcomes, and cost reductions. All right, that concludes our introduction. So now I will hand things over to John Hesemann to get us started.
Okay, thank you, Dane. So today we're going to be discussing a next generation approach to complex contaminated sites. And what we mean by that is integrating the best tools, techniques, and remediation technologies to address sites that have previously been presented significant challenges to our industry. And before we get started, I just want to mention that this approach we're going to be talking about today is really a work in progress that has evolved from our engagement with the G360 group at the University of Guelph, led by Doctors John Cherry and Beth Parker. And a lot of the concepts you're going to hear about today will be further addressed at the upcoming Battelle Conference in 2020 in Portland, Oregon. So just, I want to encourage you all to keep an eye out for these concepts you're going to hear about today as you review the program for that upcoming Battelle Conference and other conferences as well. So just to start with a brief overview, we're going to explain today why a new approach for complex sites is needed. We're going to talk about the second bullet here, what is a geology-based static model and why is it an essential first step in this next generation approach. We're also going to talk about how we integrate both conventional and next generation data sets into our static model to build what we call a process-based model. And then also, how does that process-based approach to remediation work and why is it better? And then finally, we're going to present 3 case studies that we hope will demonstrate the benefits of this approach and also the application of various next generation tools and technologies within the context of this process-based approach. Next slide. So first of all, why is a new approach to complex sites necessary? Well, as many of you know, we've struggled as an industry over the years and decades to achieve anticipated results on sites characterized by complex subsurface conditions and large dilute plumes, chlorinated solvent plumes in particular. And this, what you see on the slide here, is an excerpt from a 2019 CERTIP solicitation, and it identifies several of the key or primary causes for these challenges. So the first statement there speaks to the fact that existing conceptual site models often fail to account for the mechanisms and processes that sustain and control the persistence of dilute chlorinated solvent plumes. And the first bullet you see here, persistent low intensity source zones, these are relatively low concentration source zones, but they continue to discharge contaminant mass to plumes over long periods of time, and they have not been properly characterized in the past. The second bullet speaks to the biotic and abiotic transformation processes that are occurring at a site, and not only do these affect fate and transport, but they can also be leveraged to our advantage to support remediation. And then finally, interactions with low permeability materials. Here we're mainly speaking about matrix diffusion and back diffusion that, as we know, can significantly prolong remediation timeframes. So what does this process-based approach to complex contaminated sites consist of? Well, we call it a process-based approach, but it begins with establishing a static geology-based model, and that's what you see in the left-hand image here. And here we're showing an ESS enhanced cross-section. That's something that we use at Burns & McDonnell. That's what Rick has innovated. He's going to talk about in a minute. It's a great tool. It's a great technology. It's not necessarily needed for every site, but sound geologic interpretation really is, because the static model forms the foundation of all the data collection, modeling, and remedy design activities that will follow. So once we have the static model established, we can integrate all the other appropriate data sets that govern contaminant fate, transport, and degradation, as well as remedy selection and design, into what we call a process-based conceptual site model, and that's what you see in the center of the screen. And the end result we're all striving for is timely and economical achievement of remediation objectives. But this process is very scalable, very adaptable. It can be applied to sites of varying degrees of size and complexity. And it can also be applied, as you see in the lower right, at the optimization stage, the remedy transition stage, or when we're looking to close out a site. So I'm going to hand it off now to Rick Cramer, and he's going to talk about how we build the geology-based static model.
Thank you, John. So yes, in the approach that we're presenting today, the remediation geology component is what's about establishing a site's geologic model. And that's the part I'll be focusing on throughout the presentation. An example of this is environmental sequence stratigraphy, or ESS. Here we show the three basic steps of the ESS process, and that was presented in our 2017 US EPA technical issue paper. And in 2017, we also did a dedicated, an entire REGENESIS webinar to the subject of remediation geology and ESS. So just want to inform you that that's archived. For those who want to dig into that, drill deeper into that, it's available. So here's an example of a geologic static model, and this was presented in our case study at one of our case studies in the EPA paper. And what you see in the lower cross sections below, that uses existing boring log data to develop an understanding of the subsurface, and that's by bringing into play understanding that the depositional system was a meandering stream environment, and we were able to actually map out buried river sand channels that are encased in floodplain silts and clays. So this represents the subsurface plumbing, and these features are preferential pathways for groundwater flow and contaminant migration. And this was evolved to the point where we actually defined separate hydrostratigraphic units, or HSUs, based on the understanding of the channel deposit and the flow through the system. And what you'll see is in the lower two, we have HSU1 defined, outlined in white, HSU2, a deeper sand channel, in yellow. And the advantage of this is when you put this together in a network of cross sections, you can actually map out the occurrence of these units and these features in 3 dimensions. In this case, we have a couple plan view maps up on top that show the HSU1, how the boundaries of that channel deposit on the left and on HSU2 on the right. And again, that's key. Without this understanding of the geology, these preferential pathways would not have been understood. So now let's talk a little bit about the data types and tools that are incorporated into a geology model. So what we always rely on is whatever existing data is available. And sometimes it's boring logs. Well, boring logs are always available. Sometimes in some sites that's all. But what we wanted to also emphasize here is we bring in everything, be it high resolution site characterization data, geophysical data, any drill core. It's all brought into the mix. And what I want to show here is the final product is always to be able to interpret away from the data. That's the power of applying geology in the case of sedimentary aquifers, applying stratigraphy. And that's what we see in this, depict in this slide. The previous conceptual site model that you see above was really oversimplified versus what the kind of data and understanding that we were able to develop from the same existing data, what you see below. And after this geologic framework has been established, then still using existing data, we then use multiple lines of evidence to help further refine and validate our understanding of the subsurface permeability network. So in all sites, we have head data and contaminant concentration data. So again, that's brought into the mix. And just as an example on this particular site, the on-site contamination we were actually able to develop the hydrostratigraphic units after reviewing groundwater and chemistry data. And what we see is that the on-site contamination has migrated primarily through the HSU zone, and then laterally and vertically through HSU2, and then it discharges into HSU3, and that's the primary mode of lateral transport off-site. So this improved CSM allows us to be more strategic in assessing monitoring mass flux, in design and implementation of source and plume remedies. And now I'm going to hand off to John, who's going to explain further how we can leverage this in developing our understanding of contaminant fate and transport.
Yeah, thanks, Rick. So while we're defining the HSUs that Rick just described, we're also evaluating the processes and conditions at the site that impact contaminant fate and transport, as well as degradation, and also influence remediation design and performance. So if you go ahead and advance the slide, there's a wide variety of characterization tools and analytical techniques available to us now in the current state of the practice. And while these tools can add some cost and some time to the front end of our projects, the return on investment is substantial if the technology is used appropriately. In addition, using the static model and focusing our efforts on the critical HSUs that Rick just described allows us to be selective in choosing these technologies and in terms of where we apply them. So while focusing our resources on the transport pathways that matter, the use of this technology is more targeted and the return on investment is far greater. So just some examples that you see here on the screen, compound ratios and compound-specific isotopic analysis data. These can be used to establish degradation trends in time and space. HRSC that you see on the screen, that's high-res site characterization. This is actually a membrane interface probe, continuous log. We use these frequently to characterize source zones and transport pathways, but again, as Rick mentioned, we're developing the static model first so we can target the use of this technology, making the project more cost effective. And on the far right, you'll see the matrix diffusion, a matrix diffusion model. I mentioned earlier that can be a real challenge on a lot of sites in terms of expediting cleanup and controlling costs. So for certain sites, if we have contaminant transport pathways that are subject to matrix diffusion, we're going to focus our efforts in that area as well. So what we're trying to do with all this data, we're integrating this into our process-based conceptual site model, and the end result is definition of remediation design parameters. So we're trying to establish, sound remediation design parameters so that we've got all the processes properly quantified. So now we're moving into the design phase of a remediation project. So go ahead and advance this slide. And what this process-based conceptual site model allows us to do, first of all, is right-size our hydrogeologic analysis. So in the upper right-hand side of the screen here, you can see we're talking about focused fate and transport modeling. Now this can consist, it just depends on the site. Some sites, simple transport calculations are all we need. Other sites, a focused analytical model might be appropriate, or a full-blown numerical model on a complex site might be necessary. But again, focusing our efforts where the contaminants are and where the contaminants are being stored and transported allows us to focus that. And we can also focus any treatability or pilot testing programs needed for further quantification or testing of degradation and remediation mechanisms, and feed those results back into the process-based model where we can test uncertainties and adapt the remediation design as needed. And all of this leads to a more focused remedy based on a better understanding of the site, the heterogeneity, and the complexities. So on the next slide, just a quick example of what this might actually look like, putting this into practice. We're back to our original cross-section here that we started with, where we identify the HSUs. I've taken those off just for clarity, but we're showing the transport pathways. And if you advance the slide, if you see where the contamination is here, this might be a combined remedy that would consist of a focused source treatment, such as a thermal remedy. And in the mid-plume area, we're addressing those zones of high contaminant flux with an in situ injection of some kind. This might be a zero-valent iron amendment or some other chemical remedy. And then if you advance it one last time, further down gradient, we have zones of lower flux and more a more dilute plume. But again, we're focusing on these specific discrete transport zones, and we might be using something like enhanced biodegradation here to address the down gradient receptor pathways. So it's a very purpose-driven, focused approach that's centered on predictable outcomes and low cost. And now I'm going to hand it off to Rick, and he's going to get us started on our first case study.
Yeah, thanks, John. This case study is Eglin Air Force Base in Florida, where there is chlorinated VOC plume that occurs in underlying coastal plain deposits. Now, this project was a performance-based remediation contract that had established performance criteria to reduce the contaminant mass. And the remedy had been implemented and was not meeting the performance goals. So the project team was interested in trying to understand subsurface better in order to optimize and get the performance of the remedy back on track. So the objective of our work was to apply ESS to the existing data to better define contaminant occurrence and also optimize contaminant extraction locations to improve mass removal. So what you see in here was the original representation of the original conceptual site model. And in this case, we have boring logs and also some high resolution site characterization data. But these primarily just post the geology and hydrogeology data without a significant amount of interpretation between the data points. So this is what you see below was after our environmental sequence stratigraphy analysis in understanding the depositional system and applying that understanding to be able to map and predict and correlate between the data points. So a network of cross sections was developed, and generally speaking, it was predominantly coastal plain and sand deposits. But what was identified was a significant, previously undefined intermediate clay occurrence that we were able to map out. And what I circled in red was the response that was apparent in the geophysical log. And that particular cross-section intersected continuous layer clay, but what you could see in this cross-section that there are areas where the intermediate clay had been eroded and there was incised valley fill sands. And what's significant here is in those areas where the clay was breached, the upper sand body, a hydrostratigraphic unit, was in communication with the deeper zone. And again, when developing a network of cross sections, we're then able to map out this clay occurrence in plan view. And this became significant in understanding contaminant pathways and giving the remediation engineers an opportunity for optimizing. And that's where I'm going to hand off to John.
Yeah, so this slide here shows the locations of 2 new extraction wells that were installed to optimize the pump and treat remedy at the site. And well number 1 was located within the boundary of that clay layer that Rick just mentioned. It was screened exclusively beneath that clay layer to target the deep PCE plume you also see on the map here. Well number 2 was screened within the incised valley fill to target the lower concentration intermediate PCE plume that you see on the map. And if you go to the next slide, this is well number 1 in cross-section view. You can see it's screened beneath that clay layer. And go to the next slide. And this is well number 2, also screened down in the deeper interval, but within that incised valley fill, so it's in hydraulic communication with the intermediate zone above and that contaminant plume. So if you go to the next slide, we're going to look at the performance of these 2 wells. So in the upper left, you'll see the depiction of the intermediate PCE plume prior to installing the optimized remediation well number 2. And you can see the groundwater flow direction to the south-southwest. And you can see this plume is somewhat spread out. It's got a down gradient lobe, a cross gradient lobe, an up gradient lobe. And after 1 year of operation, if we go to the right-hand side, you can see the plume has contracted, consolidated quite a bit. That down gradient lobe is gone off to the west. That lobe has dramatically diminished. In the up gradient direction, you'll see the concentrations are actually increased, but that is due to water table fluctuations in a former source zone that causes concentrations to increase and ebb and flow over time. And the increase is really on the order of about 10 parts per billion. But overall, really good results in terms of retracting the plume and consolidating the mass. So down on the lower left, this is the before image of the deep PCE plume. And you can see there's really 3 hot spots within that plume. And then as we go over to the right, we can see that 2 of those hot spots have been diminished significantly, and the center of mass has really shifted to where that optimized extraction well was installed. So then if we go to the next slide, here we can see a graph that shows modeled and actual mass removal rate trends. So the blue dots represent the modeled mass removal, and what we're looking at here is PCE mass remaining over time. And the orange dots and trend line represents the actual mass removed. And what you see, the orange dot on the far left, the 44.9, that was data collected right before these new wells went online. And you can see the trend line quickly diverges and shows, if you advance the slide, shows significant mass removal rate enhancement. And I want to point out that this was done with no increase in extraction capacity at the site. Extraction capacity was reallocated to these new wells, so we were able to achieve significant value without adding cost, treatment costs, or pumping capacity costs. And I do want to thank Mark Stapleton with Nobles who provided this data for us. And I'm going to hand it back to Rick.
All right, so our next case study is a former Nike missile site in Ohio. And again, I'll set up the geologic framework and then hand off to John. This geology map shows that it's underlain by glacial geology. And again, we have a chlorinated VOC plume, this time associated with the former missile silo structure. So the challenge was, one of the challenges was working in bordering agricultural area, which required temporary monitoring wells. But what we show here is the original inherited conceptual site model, which had used groundwater head data to define groundwater flow direction, and then mapped out the plotted contaminant chemistry data. This specifically shows vinyl chloride and how that migrated off-site. And this shows the TCE and how that was limited to the source area. But again, getting back to the geology, so applying environmental sequence stratigraphy, identified 4 major geologic units that we were able to map from the top down. We had a till deposit, and then glacial outwash sand and gravel, coarse grain deposit, which was of particular importance. And then that's underlain by lacustrine clay, and then low permeability bedrock as well. But what's really important here is when you look at the missile silo, was mapping out the backfill of the missile silo and see how that intersects these natural deposits as well. So that's key to the pathway for contaminants and precipitated groundwater. And so a particular interest is the coarser grain sand and gravel. And the map in the lower right shows the orientation of this cross section, which was pretty much going around the direction of groundwater flow. Now in the map in the lower right, you see that this is perpendicular cross section, just to give a good understanding of the geometries of these different geologic deposits. And again, with a particular focus on the more permeable sand and gravel unit. And with that setup of the CSM, I'm going to hand off to John to talk more about the remedy approach.
Okay, so applying the contaminant concentration and redox data to the static model that Rick just reviewed, we can see that within the silo backfill, TCE concentrations are elevated up to 2,000 parts per billion, and vinyl chloride is near or below the laboratory detection limit. And conditions are also oxidizing, and that's primarily the result of seasonal infiltration of rainwater. As we progress down the groundwater flow path and through that glacial outwash sand and gravel unit, within about 100 feet of the silo, we can see the conditions become dramatically more reducing. We've got very low DO and negative ORP, and the TCE is rapidly degraded. We don't see any TCE detections. But vinyl chloride, conversely, because of the dechlorination process, actually does increase above 10 parts per billion. And this change in condition and compound ratio can be attributed to the organic content that we found in the glacial outwash HSU. So moving further down gradient, the vinyl chloride concentrations decline below the MCL, and this is providing evidence of complete degradation at the site. So then if we go to the next slide, here we're basically mapping, we're using analytical data collected over multiple monitoring events to map out the plumes. The pink is the vinyl chloride plume that extends off site, and the blue is the TCE plume on site within the source, near the source zone. And basically what we're showing here, we also have these Isopach lines. So the yellow lines show the boundary of that glacial outwash unit, and it pinches out to the north and south of this main vinyl chloride plume, and that's showing the geologic control on the contaminant plume itself. And then there's an orange 5-foot contour that shows the maximum thickness of that glacial outwash unit. So also by analyzing or evaluating multiple data from multiple events, we were able to demonstrate plume stability and provide further support for MNA as a final remedy at the site. So if you advance the slide, you can see this was the former understanding of the nature and extent of the vinyl chloride plume, and you can see it's changed dramatically. And then if you go to the next slide, the other thing this allowed us to do is make a strong case for drastically reducing the monitoring obligation for this site. So all the wells highlighted or encircled in red were proposed for removal from the monitoring program, and this represents significant cost savings because this is an active agricultural field. All of these wells had to be installed and removed during every monitoring event. So this was a very successful use of multiple lines of evidence to optimize monitoring and make a strong case for MNA. And I'm going to hand it back to Rick for our final case study.
All right, yes. So a little differently, this one addresses an LNAPL release. In this project, we were brought aboard after the initial intense field program that followed the recognition of their release, where there were about 50 boring locations which were converted to either extraction wells or monitoring wells to both characterize and provide initial recovery of the LNAPL fuel release. And the way the LNAPL plume was evaluated was based on mapping out the thickness, product thickness in the wells. And that's what you see in this map. First, the release area, and then in pink, the extent of the LNAPL plume. And as a little time went by, they identified that there was migration of the LNAPL plume at depth and to the east. And there was really no clear understanding of the reason or mechanism. So again, that's where the focus on a geologic model comes in, and that's where we were brought into the project. So I'm going to show you how we developed this fairly complex migration conceptual site model by applying ESS. And as usual, it starts off with the first step is understanding the underlying depositional environments. And in this case, the site was underlain by meandering stream channel sand deposits and floodplain silts and clays, and then also a delta sand and clay bodies overlying that deposit. So our first step was, oh, there we go. So I'm sorry, this was, these next slides are going to show how the stratigrapher was able to map out 10 separate sand bodies identified from A to J. And what you see on the left is the depiction of the stratigraphic position, the cross-section of these sand units. And on the right are maps of the extent of sand in yellow. And then at that particular horizon, the associated LNAPL occurrence. And so I'm just going to quickly go through that to show that what the stratigrapher had done was develop a network of cross-sections that included every one of the wells that were installed. And at the top, you see in brown, that's the erosion of the delta system into the meandering stream. Now, what's shown here and is important are some of the secondary features that impact subsurface fluid migration. So the fractures, those were first looked for or identified based on the structure, regional structure showing high angle faulting, and then actually being able to define fractures in the boring logs themselves. So those provided vertical pathways for LNAPL. And then also shows cemented zones, which were identified in boring logs, which were barriers for flow. And another important comment here is that this was entirely in Veda zone, so groundwater table was not encountered, although there was occasionally some perch groundwater. So this shows the completion of the conceptual site model, understanding how contaminants potentially move from the site of the leak down to depth. And we're going to focus on that area to the east that was a concern. And I mentioned there was a network of cross sections, and all of these cross sections had, like what's shown on this slide here, is all the subsurface data available was incorporated into the geologic cross sections. So we had the capability of doing interrogating the data in detail and understanding the spatial relationships with multiple lines of evidence. But I'm going to simplify a cross section and just to show you that how we were able to use all those data in order to identify contaminant, the LNAPL pathway to depth and to the east. So in this cross section, you'll see the sand bodies are identified per the letter designation. But what we were able to do was trace from the A sand over near the source area, sort of a stair-stepping migration down to the depths of the H sand off to the east. So this was key not only for this location but just for migration in general. We now had a real clear view on how LNAPL was moving through the system. So John, you were going to talk about some of the opportunities for remediation with this improved geology.
Yeah, so in terms of how, if you could go back to that slide real quick, in terms of how remediation was actually conducted at this site and how this process-based model really affected that or influenced that, the mapping of those sand channels that Rick showed, as well as the LNAPL bodies, was used to guide the siting and design of LNAPL recovery trenches, and this was really important because this was a time-critical remediation effort. This release occurred on private property. And then also this easterly expansion that you see on this cross-section of the LNAPL impact was of significant concern because it was not only traveling in a direction that was hard to understand, but it was traveling deeper. So as Rick said, integrating all of this data allowed us to understand that, and we're using this part of the conceptual site model to site and design additional multi-phase extraction wells to address that part of the plume. And another thing I just want to mention, this is a lot of work, obviously a lot of data review and analysis and interpretation, but because of the time critical nature of this remedy, this project, all of this work was done in a matter of a few weeks. So it can be done in an efficient and timely manner. So if we go to the next slide, I believe we're going to go ahead and wrap up this part of the discussion. And so we're showing here again kind of the steps in this next generation process. And I just want to say again, you know, a key takeaway is that the static model is key. Make the most of your geologic data. Don't underestimate the value of that. Even if boring log data is all you have, it really is key and adds value throughout the process. And anytime you collect additional data that can be used to update that static model, that's always a worthy effort also. And then building a comprehensive process-based CSM is worth the investment, particularly if it's done in a focused and efficient way. And we're not just saving money on the back end by doing that, but while we're collecting this data and employing more advanced interpretation and design practices, we're focusing the effort where it's needed because we have a solid static geology-based model. So hopefully this presentation has provided a helpful overview of this next generation approach. One important point I would like to make is that these concepts and these practices will become even more important as we begin to address emerging contaminants such as PFAS. So be on the lookout for these things to be discussed in that context. And then I think now if you advance the slide, I'm keying in on data collection and design verification because that's what Craig Sandefur with REGENESIS is going to speak about now.
Thanks, John. My name is Craig Sandefur, and I was introduced earlier, so I'm going to spend my time talking about technical stuff and not about myself. I'm going to synthesize down the practices, the premises, and the overall approach that you've seen today into a few distilled pieces that I have found to be very, very helpful to us at REGENESIS in terms of design and remedial outcomes and performance. So what I want to share with you today is what remediation practitioners need to know. I want to provide a few tools for you to better understand your geologic conditions. I'll talk a little bit about our design verification program, what it is and why it works, and then a little bit about passive flux meters. So as John and Rick have eloquently laid out, remediation practitioners need to know the organization and position of contaminant storage and transport units. These are fine grain, coarse grain interactions. I'm really interested in how the sand is laid in and how much of it's there, how well sorted it is, and its positional orientation to mass diffusion and back diffusion in particular. Another very important point is the scale of remediation required. When you're working with heterogeneous aquifers, you really need to untangle that piece as you've seen previously to identify the flux zone and define it carefully, because that's where the action is. So at REGENESIS, we developed this design verification program to help us identify technical blind spots It really helps us refine the design assumptions that we're making when our consulting partners send us in information. Helps us make better decisions about reagent selection. And very importantly, it helps us calibrate reagent design. So that is, we're marrying up the contaminant mass versus the reagent mass stoichiometrically. And then actually, can we fit the reagent volumes in the target treatment zone that we think we can? And so we need to identify hydraulic limitations. Very, very, very critical. So some of the things we use in design verification that we have found to be very helpful, and I'm only going to talk about 3 or so. One is continuous soil cores. You need to use geologically based soil type descriptions, and we use settling tubes. Very important component. And I will put out there that there is no substitute for continuous core data. And in fact, I would say if you could do continuous core and tie that to geophysical methods, you're far better off. You need to have high resolution, good geologic descriptions, however you can afford to get those. We also use passive flux meters, which I'll talk about in a moment, and hydraulic testing. So the settling tube, one of my favorites. It's cheap, it's inexpensive, it's semi-quantitative when a field geologist that's trained is using this and for descriptions. It's visual. It allows you to get sand particle sizes, sand silts, clays. It gives you grain size as well as sorting. It's simple, reliable, and rapid, and you can collect these at high density. And finally, it decreases that subjectivity in the, is it a silty sand, sandy silt, is it clayey, how much is there, what kind of sand do I have? It really, as you can see to the right or to the left, you can see there's a just good old gravity going to work for us, coarse grain, fine grain, all the way up into the clay layer. If you put a ruler by that, you'll have a general idea of the sorting. Hydraulic injection. Well, folks, this is really important because it documents the acceptance rates and volumes that you can actually put in the ground across the target treatment zone that you've determined using previous methods. And it assists in application decisions. So if you're using direct push or injection wells, if you're using direct push, you really like to know whether you should do top down or bottom up. If you're using injection wells, you need to really know where to screen those before you start injecting materials. So, and the final point there is field validation volumes vary tremendously from the estimated volumes that we make sitting in our offices. 90% of the time we're changing something in terms of volume. Now, further to the notion of heterogeneity and defining flux zones, passive flux meters. These are self-contained permeable units. They're designed to be inserted in a 2 or 4 inch well. They're filled with carbon. The carbon is preloaded with multiple tracers with known sorption. So essentially what happens is the tracers are displaced at a rate that is proportional to the groundwater flux. So you leave these things in for a couple of weeks. You come back and sample them, and then you send them off to the supplier where their tracers and the contaminants are measured. And essentially, they're going to tell you how much tracer and contaminant is there, and they're also going to tell you what the velocity is from that and how much mass is passed through it. So essentially, you're defining the mass flux zones that really matter in terms of shape and size of plumes. So here's a classic set of data that you get back from the supplier. I'd like you to pay attention to monitoring well 1. Across the top, you have the well ID, depth below casing, Darcy velocity, TCE flux in milligrams per square meter per day, and the groundwater velocity as a seepage. Now, in case you haven't thought about flux very much, that milligram per square meter per day is essentially what TCE is moving past a plane of compliance that you've arbitrarily established in the aquifer that cuts perpendicular to the strike or the long axis of the plume. So that is your milligrams per square meter of that flux zone per day. Now, in the red, I've highlighted the high mass flux zone of 53 and 31, with a groundwater seepage velocity of 556 and 375. Now, all of us good geologists would say, all right, that's great. But look down below in the blue. You have a groundwater velocity of 583 and 716, both entirely greater than the upper two. And you only have 2.5 to 9 milligrams per square meter, an order of magnitude less. What I'm trying to make my point here is that you can't rely on clean sands and knowing where all the flux zones are if you're going to emphasize the in situ zone that matters most. You really need to know mass and flux, particularly in heterogeneous aquifers. To kind of drive home this, across the x-axis is the factor of velocity and data separation. What I'm portraying here is the difference between a passive flux meter groundwater velocity and the estimated groundwater velocity using traditional methods. So this is just a gross differential. It could be higher, it could be lower. But across the bottom is the factor. So that's 0, 5x, 10x, 15x. If you cast your eyes across that, you can see that most of the variance is between 0 and 5 times. But I contend, even if you're 1.5 times to 2, you're going to be in trouble designing an in situ remediation barrier or reactive zone. And even at 1.5, you could be in trouble. But only 3, let's give it the 1.5 is acceptable. 3 out of the 18 sites are anywhere close to what we estimated. Further to this end, we did a massive just data assessment. And here's the take home. Gravel sites appear to have passive flux meter readings that are 3 to 4 times lower than the seepage velocity that we calculate in the office. On clay sites, we have PFM readings that are 10 to 15 times higher than the seepage velocities that as estimated in our office. Now I have a reason for that, I think, but and in the sand and the bedrock sites, that shows the greatest variability. And I think what Rick and John have pointed out, that on these clay sites, you have these incised zones, you have small partings that are continuous, and the velocities moving through those small flux zones are very high. Finally, in my final slide, design verification just in general, 44% of the time we find unidentified hydrogeologic conditions. 21% of the time, lower injection rates and ROIs, or we find an unidentified contaminant transport unit. Wasn't even there before, or it was, but it wasn't identified. 26% of the time we have a thicker contaminated zone, and almost 20% of the time we have higher contaminant concentrations than we originally thought. And what I would leave you today is that if you're wrong on any one of these, and certainly wrong on 2, your remediation project is probably not going to turn out as well as you'd like. So I would make my final comment. With the application rates in situ hovering in that 30 to 40% success rate, if you really want to get on top of it and improve success, take to heart what John, Rick, and myself are talking about, and define your flux zones, define the ones that matter, and worry about those. I'll leave you with questions.
All right, thank you very much, Craig. That concludes the formal section of our presentation. So at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a couple of reminders. First, you will receive a follow-up email with a brief survey. We really appreciate your feedback, so please do take a minute to let us know how we did. Also, right after the webinar, you'll receive a link to the recording. All right, so let's go ahead and circle back to the questions. If we are not able to get to your question, we will make an effort to follow up with you after the webinar. All right, so here's a question. This one is for John. And the question is, can you expand on the significance and application of DO and ORP in interpreting groundwater data?
Yeah, certainly. So on the example we gave of the Nike missile silo site, what we were able to show is that the redox conditions, so that's oxidation reduction potential, were commensurate or were consistent with changes in the contaminant concentrations and also the ratio of parent to daughter compounds. So in the missile silo itself, that would be the source area, we had oxidizing conditions characterized by high dissolved oxygen concentrations above, I think it was 2 milligrams per liter, maybe significantly above that, as well as positive or plus 50 millivolts or higher, maybe even it was greater than 100 millivolts, ORP, which is oxidation reduction potential that we measure in the field. And also in that same area, we had elevated TCE, which is the parent compound, and very little to no vinyl chloride, which is the last degradation product in the chlorinated hydrocarbon sequence. But then as groundwater was discharging into that natural glacial outwash unit, you could see that within 100 feet or so, there was a dramatic shift in redox conditions. So dissolved oxygen was significantly depleted, ORP became quite negative, and those conditions are favorable for the bacteria that naturally degrade the chlorinated solvent compound. And so you could see that that was in fact happening because TCE, the parent compound, was degraded to non-detectable levels, but then vinyl chloride was building up due to the dechlorination process. So we actually saw vinyl chloride increase above 10 milligrams per liter, and the drinking water standard is 2 milligrams per liter. So that's really the importance, is that it provides multiple lines of evidence that dechlorination and natural attenuation is actually occurring.
All right. Thank you, John. So another question, this is more comments. It is water level information on the case study cross sections would be helpful to prepare a hydrogeologic cross section.
Yeah, great comment. I think what we probably showed here, or what we saw, was a focus first on developing the geologic cross sections, and those are done with the lithology data. But without a doubt, once we define the geologic framework, then exactly is what's needed, is incorporating then the hydrogeology data along with the chemistry data. So
yeah, and I know we moved pretty quickly through these. If you watch the recording, if you look closer, you'll probably see there are water level indicators or groundwater potentiometric surface lines or contours on most of them. I do want to point out on the last case study for the LNAPL site, all of that was essentially in the unsaturated zone. There was some perched water within some of those sand channels, but that was essentially an unsaturated zone issue.
All right, so here's another follow-up question regarding the ORP. What are the biggest limitation in tools for measuring ORP and DO for building these types of models, and where do you see room for improvement?
Oh, great question. So ORP is a difficult parameter to measure in the field. It uses an electrode that is not ion specific, so it sort of treats all ions the same. And so I might have that backward. No, I think that is right. Or maybe it's that it prefers certain ions. But either way, there are, and you can look at Dr. Paul Trotniak. He is developing a better method of evaluating ORP in the field. But even with the complications in measuring ORP, if you have a lot of data collected over time, you can look at trends, and that's really what's important, is trends in time and space, more so than the actual measurement itself. So it's still a useful parameter, even though there are some complications with the electrode measurement devices that we use. Dissolved oxygen is another parameter that can be difficult to measure in the field. It can be measured very accurately, but you have to make sure your field teams are using the instrumentation appropriately and doing the calibration they need to do. It can be particularly difficult, and I don't even recommend doing it in direct push borings that haven't been completed as a well, just because of the different agitation and disturbance that happens can affect DO measurements and make it difficult to get accurate data. But yeah, good question. All these interpretations are only as good as the data that we're using.
All right. Okay, well, thank you, John. Let's see, I'm getting a couple of questions regarding cost. So the first one here is regarding the process-based model figure that we had shown earlier in the presentation, showing HS1 and HS2. I'm sorry, HSU1 and HSU2. What were the investigative costs for that and the cost to assemble the 3D model? And then just a more general, what percent additional cost should be accounted for when moving from a standard remediation plan to one based on a deeper, more detailed analysis that you're talking about?
All right, good question. So first of all, the focus is on the geology and using existing data. So the costs do not involve any additional data collection. It's mainly about gaining more value out of the data that you already have by an improved assessment, analysis, and interpretation of the data. So the cost is really just it's labor hours for, in the case of environmental sequence stratigraphy, the team putting together probably, again, data driven. So when we work on Air Force bases and you have incredible amounts of data, then there's going to be a big cost that's just about the getting the data in a means that can be evaluated. But for most of our commercial sites, that's not quite as big of a challenge. And so again, that's labor hours, and then it depends on the degree that the evaluation needs to be done. I think an example might be the Eglin site. We work with the client initially by showing what we can do with existing data and compare an ESS-based cross-section compared to any existing conceptual site model cross-section for the site. And in that example, initially there were just a couple cross-sections that were done, that were prepared, and then when additional questions were asked, then a more full set of cross-sections were put together. But generally, I'd say for sites at that scale, when you're talking about less than 100 feet and maybe 50 or so boring locations, that's in the order of 20 to 50 grand. And then when you're talking about working on the level of maybe Air Force base or something with a lot of data, then that could get up to the order of $100,000 to $200,000, and that would not only include the geologic interrogation of the data, but that's also including evaluating the hydrogeology. But to back up to the beginning, it's all about getting value from the existing data. And these projects never go forward unless it's obvious to see that it's going to have an impact on the direction of the site strategy.
All right. Well, thank you very much, Rick. That's going to be the end of our chat questions. Okay, wait, it looks like we're getting one more in here. This one's about ISCO and using Persulfox and ORC in open excavations. So maybe, Craig, this is a good one for you. This person's talking about their site. In shallow groundwater bearing zones, typical in southeastern Louisiana, what are the benefits and practicality of using ISCO, Persulfox, and ORC in open excavations following source excavation and removal? And what hydrogeology is needed in determining the amounts and quantities? They're saying specifically, they're talking about chlorobenzene.
Oh, chlorobenzene. Well,
Yeah, ISCO aerobic would be reasonable. It has to do with the redox setting of the aquifer itself. If you're trying to connect with the surrounding aquifer away from the excavation, and you're in tight Louisiana clay, organic rich, it's going to be fairly reduced. So you're going to need to go with some sort of ISCO agent and be ready to do multiple applications over time. If you're only interested in taking care of the excavation and the water in the excavation, Persulfox would be a great alternative. ORC would be fine, but it really depends on the concentrations that they're talking about. If they've got really high concentrations, ISCO, Persulfox, Regenox, all of those would work really well. If they're interested in, low levels, then bio might be an alternative. It really needs to be in front of a design engineer before we can make that call, and depends on a whole lot of other things like, I'm assuming they put in clean backfill, gravel, which doesn't react much. If you get in with native backfill, you can get a lot of SOD issues that can train wreck some projects. So it's all about understanding the details. So.
All right, great. Well, thank you, Craig. So that is going to be the end of our chat questions. If you'd like more information about environmental services from Burns & McDonnell, please visit burnsmcd.com. If you'd like more information about remediation solutions from REGENESIS, please visit regenesis.com. And thanks again very much to our presenters, John Hesemann, Rick Cramer, and Craig Sandefur. And thanks to everyone who could join us today. Have a great day.